One thing I want to emphasize, which I said before, but I'll say again, the answers on WebAssign need to be exact. So if the answer is 1/3, 0.33 is not correct. If you got burnt by that on the first assignment, ask your teacher and say, I didn't know any better, and we'll give you the points back. In general, we don't want to do that, but since it's time to learn stuff until you get the hang of it, if you feel that you've been robbed by the grading on WebAssign, do an ask your teacher. We'll look at your answers and we'll decide whether you were robbed or not and give you your points back. It's not our goal to beat you into the dirt. It's our goal to measure whether you know how to do this stuff. The second assignment is due on Wednesday morning, so just about 48 hours from now. The extra credit has now expired, so now every question is worth 1 point. Anything you haven't answered over the weekend was worth 1.5. And I'll put up the next assignment pretty soon. That will be due the next Wednesday. And extra credit goes until Sunday night. Any questions? Issues? Stuffs? No? Okay. I think my battery's sad. Okay, so this is going to be our first full week of classes. Nice change. So if you remember what we've been doing is working on techniques of integration. So it's still sort of here. Okay. Last time we did a lot of substitution. You did a lot of substitution. No, the next homework assignment does a lot of substitution questions. But at the end of the class, I introduced the idea of integration by parts. Which is essentially the product rule written for integrals. So it says that if you have an integral, so I'm writing it in its usual form, which looks like a function times the derivative of another function, then this is the product of those two functions minus the integral of, now we get to take we get to integrate this guy and take the derivative of this guy. There are a number of little mnemonic methods that people may have learned, like the Zorro rule and little tables and things like that. That's fine if you want to use them. The problem with, say, the Zorro method is if you write something in the wrong place, then Zorro gives you the wrong answer. The same thing with memorizing a form of a table. If you write the form of the table wrong, the answer is wrong. So let me remind you, this is just the product rule written sideways, right? The product rule says that the thing is the derivative times the thing, a product of two things. So let me just write it this way. So the product rule for derivatives says, let me just write primes, I guess. UV prime is U dV plus V du. And so if we just integrate the product rule and rearrange, we get this. And it's just another way to get the product rule. So essentially, even though we're going to focus on techniques of integration for another week or two, there's really two techniques of integration. There's substitution and there's parts. That's pretty much it. You don't know this backwards. substitution, which we did last week and you did in your previous course. Substitute. I lose my place when I start writing. Substitution. Integration by parts looks like just some silly formula. It's a very powerful technique that lets you rearrange something into terms of something else. So does substitution. So let me do a few examples of integration by parts. So say the integral, I don't know, let's do something easy first. X times the sine of x dx. So the trick in parts is we want to look for one part, which is u, so that du is simpler, whatever that means. And another part, so that's the derivative part, is an integral you can do. So, looking at this, there's sort of, to my mind, two obvious choices, only one of which works, the other one makes it worse. Anybody want to make a suggestion what I might let u be? X, right. So if I let this be u, well, actually, let me write it nicely. So I'm going to let u be x, and then once u is x, dv is forced on you. And again, it's important to write the dx, because if you don't, then sometimes you forget which one you're integrating and which one you're differentiating, and I don't know. It's not as important as in substitution, where the dx actually measures something. Here it's just reminding you that this is the derivative of a thing. So if u is x, then we need to know what du is. So what's du? So I'm hearing a few people say 1. It's not 1, it's 1 dx. So it's just dx. And then v, if dv is the sine, then the integral of the sine is the cosine, except it's negative. So v is negative cosine. There's a plus c, but I don't care about it at this point. And so now, I guess I'll move over here. So now we have, using parts, the integral of x sine x dx is, and then the formula tells me it's this times this minus the integral of this times this. So that's the Zorro business, I guess. I don't know. So it's uv, so u is x, and v is cosine x. Did I lose a minus sign? Yeah. Well, it's there, it's just not here. And then it's minus the integral of v, which is a minus cosine x. Let me put the minus sign here just to emphasize. dv. And dv is just dx. So here it's important to remember the dx so that you don't wind up with an integral without a dx. And now this is an easy integral. Just the integral of the sine, we just did it. So this is minus x cosine x. Minus minus is plus. And then when I integrate cosine, maybe I don't, let me not do that. The integral of minus cosine x is minus sine x. And then I get a constant. So the full answer, x cosine x plus sine x plus a constant. Okay? Anybody confused? Have a question? How many of you have done integration by parts before? Okay, so I guess maybe I don't need to belabor this. How many of you have not done integration by parts before? Well, then I do need to belabor. Okay. Did anyone raise their hand both times? So this technique is, pretty straightforward. The hardest thing in integration by parts is picking out what is good to do first. Let me do another example. So this one, integral of the log, doesn't look like something you can do. There's no substitution to make, unless you're really clever. They're sort of, I don't know, but in fact there are two parts sitting there. And they're parts you can deal with. Let's make this be a clicker function. So, stop this one. Stop. Where's the stop button? Stop this one. Stop this one. So let's see. So A, let's let U be the log. B, let U be 1. C, let U be dx. D, let U be 1 over x. And E, you just can't do it. Okay. So I think I have all the answers except hers, so she's going to hurry. And then she's going to wave at me when she's done. Somebody keeps changing their mind. 15. You stop, whoever you are. Can you change your mind a few more times? There it goes. Up, down, up. You can't see the little graph going up and down. I guess I should check. Did you get it yet? Oh, and then changed again. Okay, I'm stopping the clickers. You getting it? Okay, so I'm stopping them both. Stop, stop. So 68% think it's this, and 13% think it's this, and it's none of these. Okay, so there are definite parts here. There's this part and this part, and if you use the little rule that's over here somewhere, if we take the derivative of the log, it becomes 1 over x, so that's something simpler, I guess. 1 over x seems simpler to me than a log. And we can integrate dx to get x. So this would be a good thing. If we try this, when we take the derivative of 1, we get 0. That's not going to be so nice, because then we'll just get that the integral is 0, and then we can't integrate log x dx anyway, because that's the whole point. So again, we don't know what to do. So if we use b, so I'm going to let u be 1, and then so I guess dv is log x dx, and then du is 0, and then v is whatever the integral of log x dx is. Well, then that tells me that the integral of log x dx is, wait a minute, did I lose the sign somewhere? Oh yeah, that's right. This doesn't give me anything useful. Somewhere I'm missing a sign. I should have a plus here. Anyway, so this is useless. This is not what I want to do. And in fact, you never want to let u be 1, because it doesn't get you anywhere. So this is dumb. Sometimes you let u be dx, and you can't let u be dx either. So instead, what I'm going to do is I'm going to let u be the log, and dv be dx. And then du is 1 over x dx, and I can integrate dx to get x. And so now this becomes this times this minus the integral of v du. And x times 1 over x is 1, so this becomes x log x minus the integral of 1 dx, the 1 there, which is x log x minus x, plus a constant. Now, often, when it's easy, and I should have done it before, it's worthwhile, because derivatives are easy, to check your answer. Especially in integration, it's easy to make some stupid mistake, and derivatives are in general easy, so we can take the derivative of this and make sure we get the log back. So it's really worth doing that. So we just take the derivative of x log x minus x, and when we take the derivative, we have to use the product rule here, so the derivative of x is 1. That leaves me the log x laying around. And then x times the derivative of log x, which is 1 over x, minus the derivative of x, which is 1, plus the derivative of a constant, which is 0. And so I get log x plus 1 minus 1. So that's log x, and so that's good. So that was easy. And if I had made some silly mistake up here, like putting a plus sign, then I would get a plus sign here, and I wouldn't get 0, I wouldn't get the log back, and I would know that I made some silly mistake. So it's worth checking when it's easy. If checking takes longer than doing the problem, it's probably not worth it. Maybe it is. But here, this is an easy check. So it's worth doing. I should have checked that one, but I'll leave that one for you to check. What else do I want to do here? So sometimes parts is useful, even though it doesn't look like it. There's a famous story for anybody know who Peter Lax is? No? So he's a famous mathematician. He won the National Medal of Science about 15 years ago. And when somebody asked him what he did to win the National Medal of Science, he said, "Oh, I integrated by parts." So he used integration by parts in a very clever way to solve some partial differential equations, but you know, he just said, "Oh, I just did integration by parts." So it's a powerful technique. Okay. I know there's something else I got to do here. Let me do another one that is maybe slightly less obvious. Suppose I have something like the integral. Oh, let's do it. No, okay. E to the x sine of x dx. So here, certainly I can use integration by parts. And my rule of thumb says, look for one part that du is simpler, and another part where you can do the other part. So what should I take u to be?
Sin x.
Sin x. Okay. So I don't know that du is any simpler, but it's certainly there. And I can certainly integrate e to the x. So that's okay. And so by parts, this tells me that this must be uv minus the integral of v du. So that's minus a minus e to the x cosine x dx. Well, doesn't look like, did I make a mistake? Okay, so, oh, because I'm stupid. Yeah, that's better. I would have made the same mistake the second time around than it would have been matter, but okay. So that doesn't look like it helped, but you know, maybe we could try again and see if it gets any better. So let's try again. Not try another integral, but let's try this part here by parts. So, I don't write that yet. So now in this piece, I want to do this by parts, and I'm going to play the same trick. I'm going to let u be the cosine, and so du, now I get a minus sign, is minus the sine, and dv is e to the x, so v is dx, is e to the x, and so that means that this whole thing becomes, well, I get this from before, let me write it down again. I still have this e to the x sine x floating around from before. Let me just rewrite the whole thing. So this is from before, and then minus, and now when I do parts here, I get e to the x cosine x, and then I get minus e to the x, I get minus a minus sine x. Huh? That's right. And then dx, and I get an e to the x. Try it in order. There we go. Okay. Now that looks like we didn't get anywhere. And somewhere I have a mistake. Where's my mistake? No, there's a sign wrong. It's like G and wrong. Oh, no, there's not. It's fine. Okay. So if I distribute the negative, I get the thing equals e to the x sine x minus e to the x cosine x plus itself. Well, remember what we're doing. We're trying to solve for something. We're trying to figure out what this integral is. So that means, if I distribute the minus here, I have two of those guys, and I can just bring this one over here and add them together. To get that, well, I don't know what that integral is, but twice it is e to the x sine x minus e to the x cosine x. Well, if twice it is this, then the integral I want must be half of that. I lost my concept. So sometimes integration by parts doesn't seem to go anywhere, but you can get back where you started. Now, if I had taken the part to be e to the, if I had taken u to be e to the x, instead of taking u to be the sine, I would have gotten the same answer. Yeah?
Okay, I don't get where,
It's magic.
like, how do you know when it's done?
Well, I know when it's done because I have the answer.
Well, how do you know it's because on the top of it,
Yeah?
and it still has, yeah, it still has,
An integral equals some junk minus itself. Right? And so since I have a thing equals some junk minus itself, that means that twice the thing is that junk. Now, if I had done a slightly harder version, which I think I'll put on the homework. No! Like if that had been an e to the 2x, or a sine of 3x, or something like that, then instead of being this thing equals some junk minus itself, it would be this thing equals some junk minus 5 times itself. But this still is the same trick. I get something expressed in terms of some extra stuff plus itself, so that means I can solve for the thing I want. This is non-obvious, but once you see it, then it is obvious. Yeah? Well, supposed to. I mean, it's sort of a reasonable. So the rule is, instead of simpler, how about not worse? Because if it's the same, and it's always going to be the same, then you get back where you started. So there is an order. Essentially, the thing that you want to try letting your u be first is the ugliest thing that gets better when you take the derivative of it. So something like inverse trig is pretty ugly. And when you take their derivative, they become rational functions. Logs and exponentials. Well, log gets better, exponential not so much. Trig functions, well, they don't get worse. Exponentials, they don't get worse. Polynomials, they get better. So there is some kind of an order, and there's some, does anyone know this mnemonic? It's like, huh? I don't know. So, yeah, so there's some mnemonic that you can use. Logs are good. Inverse trigs are almost as good as logs. Algebraic? Yeah, algebraic things. Trig, exponential. So you can remember that. The way I remember it is, the thing that gets the nicest when you take its derivative is best to do first. So logs are horrible because they're this transcendental thing. But their derivative, 1 over x, come on. Inverse trig, they're also pretty horrible. Inverse tan, but its derivative not so bad. 1 over 1 plus x squared is nicer than inverse tan. Algebraic things, when you take their derivative, the degree goes down. Trig, well, it doesn't get worse. Exponentials, they don't get worse. So if you want to memorize this little thing, okay, obviously you can tell, I don't know what it is. Just think about it. Okay. So, I guess in that case, well, let me do one other example. And when it's appropriate. Okay. So this fact is true only if x is positive. But if x is negative, then we have, this doesn't make any sense. So this is true as long as x isn't 0. And we'll deal with what if x is 0 in about 2 weeks. So this is true. So when do you have to? When x is negative. If we are sloppy and leave them off, it's not wrong. I mean, most people know that it's okay to leave them off most of the time, but sometimes it's important. Did that answer your question at all? No. Okay, so let me do, say, another relatively easy one. This one is really just like the other one. I'm going to have to do integration by parts a couple of times on this one. Right? Because here, obviously, if you want to use that little formula or you just want to think about it, when I take the derivative of x squared, it becomes a 2x. That's nicer because it's a lower power. Derivative of sine, integral of sine 2x is something I can do. So, if I take the derivative of sine 2x, it becomes a 2 cosine 2x. No better, the integral of x squared is 1/3 x cubed. That's worse. So, I don't really want to do that unless I have to. So, it seems obvious to me that we're going to let u be x squared. So, du is 2x dx. We let dv be the sine of 2x. So v is, well, I have to deal with this 2, so in my mind I make a substitution. W equals 2x, so dw is 2 dx, so I pick up a half. So this is 1/2 cosine 2x, except I need it to be negative. Okay, so this becomes uv minus the integral of v minus 1/2 cosine 2x du. Du is a 2x. I'm going to move it over a little bit. And then this 2 cancels that 2, but the negative from the cosine changes the sign there. Okay? And so, well, this is almost like what I just did. Again, I'm going to have to do integration by parts to get rid of this x. But when I take the derivative of x, I get a 1, so that's going to be good. So this is, I just keep this guy coming from before. And then here, actually it's not right. Here I'm going to let u be x, so dv is dx, that's good. And, I'm sorry, that's a u. du is dx. dv is the cosine. And so v is 1/2 the sine of 2x. That. And so now, this thing just comes along for the ride. Minus x squared over 2 cosine 2x minus uv. So that's minus 1/2 x sine 2x minus the integral of v du. So v is a 1/2 sine 2x, and du is dx. We're almost done here. So that whole business is x squared over 2 cosine 2x minus x over 2 sine 2x plus, so I get a 1/2. The integral of sine 2x is 1/2 cosine 2x, except it's negative. So change the sign again. So I'm pretty sure that's right. It's probably worth taking the derivative to check. Yeah, I guess that's not. What? Oh yeah, see, that's why I should check. Yeah, I'm pretty sure that's. Yeah, because otherwise these won't cancel. Yeah. Okay, so let's check that it works. And then if it works, we'll go back and see where the bits came from. If it doesn't work, then we'll go back and see that I screwed up, which is not unheard of. as you know already. Okay, so let's check this. So, if I take the derivative of x squared cosine 2x, derivative of x squared over 2 is x, but it's negative. And then minus x squared over 2 times the derivative of cosine 2x, which is a 2 sine 2x, except it's negative, which changes the sign back. So that's the derivative of this bit. And then we have minus, this x over 2, his derivative is a 1/2. And then we have minus, oh no, I already have minus, x over 2. And then the derivative of sine 2x is 2 cosine 2x. So those 2's cancel, that'll be good. And then here, the derivative of 1/4 cosine 2x is 2 sine 2x, except it's positive. And now let's just check that everything in sight cancels except x sine 2x. Something looks wrong here already. Did I screw up? Probably. Okay, so this is a 2 sine 2x, and this is an x cosine 2x. X squared, there should be another x squared to kill this. Oh no, I started with x squared. Okay, good. So here's my original integral. X squared sine 2x is what I started with. This x cosine 2x cancels with this x cosine 2x because it's minus. One of the signs is wrong. Shit. Nobody heard that. Okay, so somewhere I made a sign error. I want this to cancel with this, but somewhere I have a negative sign wrong. Yeah. Probably. So let me just check that the other bits cancel, and that'll help me find out where it's wrong. And then this guy certainly cancels with this guy. So, what do you mean? Wait. This is a 1/2 sine 2x, this is a minus 1/2 sine 2x. So they cancel for sure. So, there's this trouble here, and she found it, which is good. So where is it? You found it, tell me now. Either of you, I don't care. Right here? That should be a plus. That makes sense. So why is this a plus? Because it's a minus minus? Oh yeah, I just copied wrong. Okay, this is why you should check. Okay, so this plus now becomes this plus. No. This plus is the 1/2 x sine 2x. Which is this one. Yeah, I can't even copy my own writing. It's good. And this still stays negative, so it's good. So now it's right. Okay. So we're checking. Yeah. The tabular method is really the same. It's the same. As long as you can make it clear what you're doing. So the tabular method is the same as this, it's just a little more organized. It's the same. The only problem that I have with the tabular method is that when you're doing something like this, sometimes, well, it works if you pay attention. What the tabular method is doing is just organizing everything in little rows and columns, and you don't bother to rewrite those things that you already have. The problem with not bothering to rewrite them until you get to the end is that you forget about them in the middle. And so you can wind up with, you need to use them sometimes. So the problem I have with all of these variations, they're fine, as long as you know what you're doing. But a lot of times they're shortcuts. Shortcuts don't always work because you're taking a shortcut through the woods and then you run into a bear trap. It's not a good idea. So shortcuts are fine as long as you understand that they're going to work. So I don't mind about the tabular method. I'm not going to teach it because it doesn't always work. I mean, it does. It's harder when it doesn't want to work. Okay. I know there's another thing I need to say. Okay. These things also work just fine with definite integrals. And usually with definite integrals, so these are ones with bounds on them, you want to, two things I need to say. So before I say definite integrals, because that's sort of obvious, suppose I have something, since I'm sticking with the sign, I might as well, let's do the cosine this time. Suppose I have x to the 23rd power e to the x dx. I am not going to do this every time. If I do integration by parts, the e to the x is not going to get any better. It's not going to get any worse. The x will become an x to the 22. Let me just do it once or twice. So we let u be x to the 23rd. So du is 23x to the 22. dv is e to the x. v is e to the x. And so this is 23x to the 22 e to the x minus the integral of 23x to the 22 e to the x dx. Let's do parts again. So if I do it again, u is x to the 22, du is 22x to the 21, dv is e to the x dx, v is e to the x. So when I do parts again, from before I have this, and then I get 23 times, and so I get 22 e to the x, uv, x to the 22 e to the x, yeah. Sorry. I'm just still too early. I haven't had enough coffee yet. This is x, it's uv. Thank you. This one's right. Okay. So here I get x to the 23 e to the x minus 23x to the 22 e to the x minus the integral of x to the 21 e to the x, except I pick up a 22 here. The pattern should be clear now. Every time I integrate by parts, I pick up a new term like this, and I get another integral with something lower. In fact, in general, rather than just doing this, let's write a reduction formula. Let's not do it. Let's not do it for any particular number. Let's do it for n. So again, if I integrate by parts, du is n x to the n minus 1 dx. dv is e to the x. So v is e to the x. So this is x to the n e to the x minus the integral of n times x to the n minus 1 e to the x dx. And now we just apply this over and over and over again to see. So now I don't have to just keep doing it. I can see that, in fact, the integral of x to the 23rd e to the x is going to be, so I get an x to the 23rd e to the x, then I lose a 23x to the 22 e to the x, and then I have this integral, which is going to give me a factor of 23. And so there's an integral in here that I'm not writing, and that's going to give me a 22x to the 21 e to the x. And then there's going to be another integral in here, which I'm not going to write. And I'm going to pick up a factor n minus 1, n minus 2, boom, 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 boom. And the signs are going to alternate all the way down to the bottom. So that means that, what am I going to get? I'm going to get x to the 23rd. Let me just put the e to the x in the front. I'm always going to get an e to the x. X to the 23rd. Then I'm going to lose a 23, x to the 22nd. Then I'm going to gain 23 times 22, x to the 21st. Then I'm going to lose 23 times 22 times 21, x to the 20th. Then I'm going to gain 23 times 22 times 21 times 20, x to the 19th, and so on, until I finally get down to 23 times 22. Let me just write 23 factorial. Times e to the x. Is that enough? Plus, right, 23 factorial means 23 times 22 times 21 times, and so on. Okay? So, what's the point of this? Sometimes it's easier just to make a formula and then use the formula over and over and over. I do not recommend that you memorize this formula because it's really easy to derive. And it's also really easy to mess up in your memory that maybe this should be a plus, or maybe this is where the n goes, or whatever. So it's really not to your benefit, except when you're using it, to memorize such a formula. Now, computers memorize such formulas, and there are certainly programs that will do formulas for you. And they just use these formulas, and computers are very good at looking up information and applying it. Okay, so one last thing to say is that I didn't do definite integrals. I'll do that first thing. It's easy. There is another homework assignment due on WebAssign on Wednesday. There's also a paper homework assignment, which you can get from the class webpage, which is due during the second recitation of this week. It counts, one problem counts more than 1 point. So it's hard to look at.